Engineering, IIT Bombay. He completed his BTech from Madan Mohan Mahavidyalaya University of Technology in 2001. He has completed MTech from IIT Bombay in 2003. He has done his PhD from Nanyang Technological University, Singapore in 2008. After prior to join IIT Bombay in March 2015, he was working as an senior researcher in the Technical Research Center of Finland, where he was responsible for develop 3D packaging technology for various MEMS packaging applications. At NTU, he developed his high aspect ratio of D-reactive ion etching, that is DRIE, etched copper filled through silicon wires. He has received Norman Hackerman Young Author Award in 2006 for his work on aspect ratio dependent copper filling process. He has published more than 40 journal papers and 33 conference papers, and he has several patents on his name. His research interests are in MEMS fabrication, 3D packaging, through substrate wires, that is VSV, and micro machining of difficult to machine material. So with this short brief introduction, I would like to hand over the session to the Dr. Pradeep Dixit sir. Sir, please.
Yes, so thank you, Ankit, for a bit long introduction. Okay, so let's do it quickly. Okay, so as Ankit has mentioned, so prior to joining IIT Bombay, I was working as a senior scientist in Technical Research Center of Finland, where I have mainly work on the area of MEMS fabrication and packaging of MEMS component. So I'm going to talk about in this session about some basic fundamental details about microsystem packaging. Okay, what is its current status? Okay, what are future trends? And if time permits, then I will show you the kind of work which we are currently doing here in IIT Bombay. Okay, so I'm going to present now the entire screen. I believe that you are able to see this screen now.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, yes, great. Yeah. Okay. So let me simply go to the presentation mode. Okay. So as I mentioned, so today's topic is going to be this microsystem packaging. Okay. So just a fundamental microsystem packaging course. Okay. We are going to talk about. Okay. May I request all of the participants to mute themselves? Thank you. Yeah. So the outline of my talk is going to be as per following. Okay, I will just introduce the microsystem packaging. I will tell you what are the basic fundamentals about the packaging. Okay, how does this basic packaging contributes in the overall cost of a product. Then I will tell you that how do you differentiate different levels of packaging. Okay, so packaging is a very common word, and it is basically used both for integrated circuit packaging. Okay, so I will tell you that how the MEMS packaging is different from IC packaging. Okay, so IC packaging is a kind of already a standard process, and I will tell you that what are the different challenges which we encounter when we talk about packaging of MEMS component. Okay, then I will tell you that what are the current trends which is happening in the field of packaging. Okay, so there are two major trends which are going on, that industries are moving from something called chip scale package to something called wafer scale packaging. Okay, so at present, when we talk about IC packaging and also MEMS packaging, we are mainly doing the packaging at a chip scale. Okay, but right now the trend is to move towards something called a wafer scale packaging to reduce overall cost. Okay, then second thing is about from the two-dimensional packaging approach to something called 3D packaging approach, and this particular trend is mainly to reduce the footprint area to make the overall device, okay, smaller size. Okay, and then like I said, if time permits, then I will tell you that that in IIT Bombay currently my research work is on the through glass via. Okay, so this TGV stands for through glass via, which is basically a three-dimensional interconnects. Okay, and how we can use it to create 3D MEMS component and how we can use it for packaging applications. Okay, so I believe that most of the participants are familiar with microelectronics and MEMS. Okay, So if you look at, we have two different like technical terms. One is what we call microelectronics, which is mainly our electrical engineering work on, in which we mainly work with the transistors. Okay, we also called it as a CMOS. We also call it FUL, front end of the line components. Okay, so if you look at this, there's a common terms which has originated. This is what we call as the microsystems. Okay, so microsystem is a general term used mainly for microelectronics. Okay, but also for a MEMS component. Okay, now MEMS has also originated from initial MEMS, and now we have a bio MEMS, we have RF MEMS, we have photonics. Okay, so all these technical terms, photonics, optical, okay, RF, they are also becoming a part of a microsystem technology. Okay, so when I say microsystems, we mainly deal with all this particular technology. Okay, so we have both. Now, if you look at this, some of the images which I have mentioned here. Okay, so everybody is familiar with this. This is basically our microprocessor. Okay, now what you are looking at here is a packaged version of a micro processor, right? So this is what is known as a packaged version. Okay. So let me write down here this packaged version. And on the right hand side, I have shown you a packaged version of a pressure sensor. Okay, so if when you look at this component here, a pressure sensor will be very tiny part, will be inside this particular here. Okay, so the technical term microsystem packaging not only deals with MEMS packaging, but also with the IC packaging. Okay. Now, it's very important for us to find out, okay, later on we will go through and we'll indicate that why the MEMS packaging is considered to be more difficult than the IC packaging, okay. So one of the main fundamental reason is that when we talk about the traditional MEMS devices, so traditional means we are talking about inertial MEMS sensors like accelerometer or gyroscopes or pressure sensors. Okay, they all have some kind of a tiny moving parts. Okay, so either you have this kind of a COM drive which are basically moving, or in case of pressure sensor you will have some kind of membrane. Okay, so MEMS has a moving parts, but microelectronics does not. So because of this moving parts, ensuring the packaging is relatively difficult. Okay. So let's look at a very quickly kind of overview of a different MEMS devices which we encounter in our daily life. Okay, I'm sure that in this workshop a lot of eminent speakers might have talked about already some MEMS devices. So I'm not going to spend a lot of time, but I will tell you that for the popular MEMS devices, for example, accelerometers. Okay, you will find accelerometers. Okay, we have gyroscopes. Okay, we have this pressure sensors. Okay, we have this digital production. This is also called a DMD, digital micromirror device. Okay, so and then we have this actually a printer. Okay, the inkjet printer. So these are the most important MEMS component which has been originated and which are commercially available here. Okay, accelerometer. You have a gyroscope which is mainly used in tablet devices. We are also using a gyroscope in our digital camera right now to detect any kind of a micro scale vibration, so that we can take this kind of corrective action. Okay, so everybody is using mobile phones, and we know that in mobile phone also when you change the orientation from horizontal to vertical or vice versa, you will see that the screen is automatically detecting it that the user is looking at the horizontal screen or vertical screen, right? So this kind of decisions is already being taken by these kind of MEMS devices. Okay. Similarly, if you this is another slide here. Okay, so if you look at this kind of gaming devices, okay, gaming console, for example, if you look at this Sony PlayStation, okay, the control, the remote control, whatever you are using it for a gaming console, it has a very tiny components. For example, this is a 3-axis accelerometer which is present in this particular remote here, right? So this is a remote control which is used for a gaming console. Okay, so now what happens is that if you look at this component, okay, again, this picture here, what you are looking at here, this is not a MEMS accelerometer, but this is a packaged version of accelerometer. Okay, so the real component is going to be relatively very small, right? So accelerometer, this kind of pressure sensor, these are the most famous now they're already commercialized. A lot of these are making this kind of components, okay, and they're working on this area. So if you look at a typical car, okay, this particular picture is coming from a Bosch, okay, in Germany, and those guys who are familiar with the MEMS process, okay. So Germany is doing very well in terms of MEMS sensors, okay. Germany is a basically hub of automobile cars, and they are making all their cars smart, okay. So what do you mean by smart? They're putting a lot of sensors, okay, and sensors are basically they can detect any kind of a change in any physical quantity, whether it's a pressure in the tires, or they can have air bag deployment, okay. We have automatically this mirror movement, okay. So if you look at this picture, so at a modern automobile, okay, this picture is about 2014 2015 time frame, okay. So at that time it is indicated that we have about more than 100 sensors which are present in this automobile, this car, okay. And out of these 100 sensors, at least 30 sensors are being manufactured by MEMS technology, okay. And what are these? Like I said, so you have some kind of pressure sensors are there, okay. We have accelerometers, okay. We have a gyros, okay. We have a micro scanners also for overhead display. Then we have different kind of infrared sensor. Slide indicates that now MEMS devices are really getting very, very popular, okay, and we will see more and more application of these sensors in our coming daily life, okay. So just give you example, those who may not be familiar, okay. So in our automobile cars, okay, if by bad luck, if we hit some kind of a obstacle, right, we have this thing what you known as a airbag, right. So everybody, I hope that people have not encountered this airbag deployment. This is not good for your health, okay. But for example, if you are looking at this particular any kind of a crash, right, so what happens is that this airbag, which is either filled with nitrogen or any kind of inert gas, okay. So we have a compressed cylinder which is present in the automobile car, okay. So the moment this particular car experience some kind of a crash, okay, this airbag will be deployment, okay. So the device which is responsible for deployment of this particular airbag is this one, okay. So this is a tiny accelerometer which is present in these cars, okay. And if you look at the size of these components, okay, this is roughly about 2 to 3 millimeter, okay. But again, this is not that accelerometer. This is what you know as a packaged version here, okay. And if you cut it down this part, okay, you will see we have devices like this, okay. And if you further zoom in, you have devices like this, okay. So this is this is the real accelerometer which is made out of a silicon, okay. So we have this particular structure is known as a COM drive, okay. And what happens is that if you look at this COM drive, one set of fingers are fixed, okay. So let's call this as a fixed, okay. And this particular finger here, they are basically allowed to move, okay. So what will happen? So whenever this body, the whole automobile, it experiences a sudden deacceleration, what happens is that the capacitance between this fixed finger and the movable fingers, it basically changes, okay. So this accelerometer find what is the change in the capacitance value, and that change in the capacitance value is correlated to the acceleration, okay. That is what has been indicated here. So if the measured value of capacitance goes beyond a critical limit, okay, the airbag will be deployable, okay. So now if you look at this again, we are talking about accelerometer here, okay. So on the background, if you look at these devices here, okay, these are the wafer scale view of MEMS accelerometer made by Bosch here, okay. And this is the packaged version. So you can see, imagine that the real size of accelerometer is about 1/4 to 1/5 of the package size. Now the question here is that why do we need packaging? Okay, what is the really need of that? Okay, so now let me just show you the cross section of this particular packaged version. Okay, so cross section is shown here, right? So if you look at this particular picture here, you will see that this one is a MEMS device, okay, and this one is a ASIC. Okay, so ASIC stands for application specific ICs. Okay, and now so this is the first important part. Let's call it 1. This is second important part, let's call it 2. And very, very important part, this wire, okay, this is third part. Okay, so any kind of a packaged MEMS device, it contains these 3 devices. Okay, we have a MEMS device. Second is going to be the ASIC or IC. Okay, and third is going to be interconnection. Okay, so what happens is that, imagine your own body, right? In our body, we are given basically this 5 sense, right? So we have eyes, ear, our tongue, which will basically test. Then we have a skin. Okay, so if you look at this case, what happens here, if you compare the analogy between a MEMS sensors or MEMS device to our body, what happens? So this MEMS device is just like a sensor. Okay, it will only tell whether a measured value of a capacitance, okay, or it will basically tell that what is the measured or what is the change in the capacitance. If the automobile body is experiencing some kind of a deceleration, what is going to be the change in the capacitance? Okay, now this is the brain. ASIC is, you can imagine, ASIC die is just like our brain. Okay, so what will happen? The signal from the MEMS device, it will go to the ASIC device by this particular interconnection. Okay, so this wire bond which you are looking at here, okay, this is very important. This is a gold wire. Okay, so this gold wire, you can imagine that in our body we have a lot of neurons, right? Neural network inside our body. So whenever we encountered any kind of a danger, okay, so for example, let's say that I'm walking on my street, okay, and suddenly I see some snake. Okay, now what will happen? Our eyes will tell that this is a snake. Okay, the information will be passed from eyes to our brain through this neuron, right? And now our brain will compare this image which it has captured, and it will compare with our stored memory. Okay, now we are being taught that snake is a dangerous animal, we have to avoid it. Okay, so what will happen? Our brain will compare the captured information through our eyes, and it will compare to the stored information. Okay, now if this comparison says no, this is snake, then what will happen? We have to take our some kind of a precaution message. So this message will be from our brain, it will go to our actuator, which is hand and foot. Okay, so we will take out this kind of precautionary action. Same analogy is applicable in case of MEMS. Okay, so MEMS sensor is going to be that what is going to be the measured value. The information will pass through the interconnection. Okay, and then it will go to the ASIC, which will take a decision whether we have to deploy the airbag or not. Okay, so if the de-acceleration is relatively very small, airbag will not be deployable. Okay, I hope this thing is clear. Okay, so when you talk about the packaging, okay, so packaging is including everything. Okay, so if you talk about packaging here, packaging means that we need to protect these MEMS sensors. We need to provide suitable interconnections, okay, and we need to protect the entire thing, including IC, from the external environment. Okay, so this part is called MEMS. Okay, this part is IC fabrication, which our electrical colleagues do, and then this is separate department which we called as a microsystem packaging. Clear? Okay. Okay, so as I mentioned to you that if you just fabricate a MEMS device, okay, it is not going to be useful, because ultimately we need to provide these devices to a end users, which is a customer, right? So the fabrication of MEMS device alone is not sufficient. Okay, you need to provide suitable ICs, okay, which will come from the microelectronics guys, and then you need to put both ASIC die as well as the MEMS die. You need to provide some suitable interconnection, and then you need to put on a proper package device. Okay, then only this is going to be applicable for a customer users. Okay, so packaging, in short, it provides an interface between a ASIC and MEMS devices. Okay, and then we will later look at that there are different levels and how we can basically connect to the outer world. Okay, so if you look at the main functions of packaging, okay, there are three. First of all, we need to provide some kind of a protection from an external environment. Okay, so let's look at this case here. Again, So if you look at this picture here, you can see that this one, okay, this picture, let's call it 1, this is ASIC, okay, and if you look closely here, okay, this is a MEMS die, okay, but MEMS die is not a single die, okay. If you look at, if I draw the picture here, okay, so what will happen? You will have a MEMS die or MEMS devices, and then this MEMS devices is basically, there's another this kind of a device, okay, which is kept here. This thing what we call as a cap or protect, okay, this is cap, okay. So this cap wafer or cap device, it basically provides some kind of a mechanical protection, okay, to the MEMS devices. As I already mentioned that MEMS, most of the MEMS sensors, for example, accelerometer, pressure sensors, gyro, they have small tiny moving components, okay. So if you do not provide any kind of a cap, okay, these tiny components might be broken, okay. In addition to that, what happens is, we do not want that any kind of a air, okay, should leak inside this particular cavity. Okay, so whenever these MEMS devices are fabricated, okay, we need to ensure that the pressure inside this particular MEMS device should remain uniform, okay, because all these MEMS devices are calibrated, okay, to a reference pressure. Now what will happen? If you do not provide any kind of a suitable package, okay, the air from the outside, it will basically leak into the MEMS cavity, and it will basically affect the performance of the MEMS accelerometer. Yeah. Can we mute ourselves? Yeah, thank you. Yeah, so okay, so this is the part, okay, mechanical protection, okay. Now the most important part is that we need to provide interconnection, okay, or electrical interconnection, because MEMS die and ASIC die, they need to communicate with each other, right? So if you look at closely here, you can see that there's small wire bonds, okay, 1, 2, 3, 4, 5, 6, okay, 6 are here, okay, 6 on the other side, okay. So you will see that this is a MEMS device, and MEMS device and ASIC device are communicating through these wires, and then ASIC die itself is communicating with outer interface, which could be a PCB, printed circuit board, or it could be anything else. Okay, same thing is here. If you look at this picture here, this is an example of a ceramic package, okay, ceramic package here. So again, there are two devices here. This is a MEMS device, this is a ASIC device, and whole thing is basically kept on some kind of a package, which is ceramic package, and these are the pins, okay. So these pins can be soldered on a printed circuit board, okay. So now if you look at, if you get a chance, if you have any old mobile phone, okay, you try to open it up, and then you will see a very nice looking print board here, okay. So this is a image of an iPhone motherboard. This is an older one, okay. Now you will see that there are very lot of devices here, okay. So we have a flash memory, okay, we have a lot of ICs, okay, and from MEMS point of view, okay, there are two devices which are basically popular ones, okay, which are kept in this accelerometer and gyros, okay. Similarly, we have this camera module, okay. So you can see that this is a camera module, and if you open it up, okay, so this is a, now we are using this CMOS camera module, okay. So this is that optical lens, and below this chip is going to be that IC chip, okay. So if you look at this part, okay, this is also an example of a packaging, okay, because packaging means that you need to integrate this ASIC chip, okay, with a MEMS camera module, and then you need to provide the suitable interconnection, okay, so through which there are going to be interconnect, some kind of a wire which are running through these things, okay. So I hope that this thing is clear, okay. So mechanical protection and electrical connection, there are two very important function of packaging, okay. Now third thing is also getting important, especially in this tiny devices like mobile phones, right? So if you look at our mobile phones, okay, you probably some of you have experienced, okay, that this battery consumption is now getting very higher, okay, and if you speak half an hour, 45 minutes continuously, or if you are playing any kind of games, okay, this mobile phone, it becomes very, very hot, okay. So if you look at our this size of the mobile phones, okay, size of mobile phones are continuously shrinking, okay. So if earlier it was a huge, now size is becoming smaller, but the functionality is really becoming going higher and higher, okay. So we do not have efficient ways by which we can dissipate heat, okay, from the, let's say, microprocessor, okay, to the outside world, okay. So this is becoming a very big challenge for the packaging guys, okay. And most of us probably know that the temperature is one of the major function which decides the reliability of a MEMS module, okay, or even in case of ICs module, okay. So if the temperature is higher, okay, the failure rate of the devices will also going to be higher, okay. That's why this is very important that we need to provide certain kind of solutions, okay, inside the package, okay. So if you look at our iPads, okay, or iPhones, okay, you will see that there is a small device called heat pipe, okay. So heat pipe, okay, is also a part of a package, okay. So heat pipe is responsible for taking away the heat from a hot spot, and it will basically reduce the temperature, okay. So I think these slides, I think everybody understands, this thing is clear that the trend is normally moving right now, okay. So earlier, if you look at our initial components, let's say about 10 years before, we used to have the components, okay, which are going to have a single functionality. So we used to have a simple phones, we used to have camera, okay, digital camera or a camcorder which can record the video, moving images, okay. Then we used to have a separate music player, MP3, okay. Then we have something, again, this kind of storage devices. But now if you look at our modern phones right now, we are somewhat here in this range, okay. So our mobile phones can not only be used only for communication, but it is also for video recording. We have a now 48 megapixel camera still images. We can take it, we can take a very high definition moving images, okay. We can of course use it for as a MP3, okay. So from a single functionality, we are going for a like multi-functionality, and this is kind of a goal we have, okay. So right now, if you look at our future, okay, so we are talking about some 2020, we are also going to incorporate more and more devices inside the same for example, right now our mobile phones, our this Apple watches, they do not have any module for a medical application, okay. But companies are already trying to work with, okay, so that we can monitor our health, okay, at an institute. It means that at same time, okay, every day it can tell us that what is going to be our blood pressure, okay, by analyzing the sweat, okay. We can tell whether what is the going to be our urea level, okay, what is going to be the salt level, and so on. So people are already working on this kind of devices. So a single device can be used for a multifunctional things, okay. So the problem is that although we have this individual devices are already being available in the market, putting all those devices in a single product is a major challenge for packaging engineers. This is where a lot of things are going on. So now just look at this. When we talk about any kind of a micro system packaging, okay, there are different levels, okay. So if you see here, I have mentioned 0th level, okay, first level of package, second level of package, and third level of package, right? So these the classification of different packages are happened based on the interconnections. So these are the connects, okay. So how do these chips, they communicate with each other, okay? Depending on that particular interconnect, okay, we can classify the packaging at a different modules, okay? So 0th level package, that happens at a chip level itself. So if you look at, for example, any kind of a IC chip, okay? So we have an example of a chip here, Okay, so you have a silicon wafer, and you can see there's some square shapes. So each square represents a individual identical chip. Okay, and within a chip, if you are providing interconnections, that is called as a zeroth level of package. Okay, now if what we do normally, okay, we do the dicing process, we get individual chip which is basically working, which is giving a output performance as per the desired one, and then we have a different kind of a package which is basically available. Okay, so if you look at this thing, okay, this is a what we known as a pin grid array, which is mainly used for a microprocessor chip. Okay, so this is pin grid array carrier, because you can see there's some pin here. I will show you example. Okay, so either you can take this kind of a package, so either you can put a single chip, okay, or you can put a multiple chips on the same package. Okay, so if you look at, let's say that this is a chip here, okay, and I have, this is a carrier. Okay, so this is a single chip, this is a carrier, or let's call it package here. Okay, so what people do, they first put this chip on the package. Okay, they use something called die attach material, and then depending upon what kind of interconnection you have, so they can either go for this kind of a wire bond, okay, or there's something called flip chip, which is basically a solder based technique. It's called flip chip. I will have some pictures which I'll show you later. Okay, so okay, and after that we can put some kind of epoxy. Okay, so we have some kind of epoxy on the top of that. Okay, so if you look at this whole chip here, okay, this is an example of a first level package. Okay, so inside that there is going to be a chip will be provided some kind of interconnection and some kind of a mechanical protection, right? Then we can take this first level package, we can put it on a some kind of smaller printed circuit board to make it as something called a second level of package. Okay, and then this second level package will be inserted in a main motherboard, and that is what as called as a third level package. Okay, then we have a fourth level package and fifth level package, which from the technical point of view are not so critical. So when we talk about the core technical difficulties, technical challenges, we are mainly talking about from the packaging point of view, first and second level of package. Typically, this zeroth level of package is a concern for microelectronics guys who have to create interconnection within the chip. Okay, so let's look at a couple of examples of a first level of package. So like I said, so you can see that this is a MEMS accelerometer, okay, from a company called Sensonor, which is a Norway-based company. And like I mentioned to you, so if you look at this picture here, we have three dies. Okay, we have ASIC. Okay, so this is one is called ASIC or electronics chip, and then this is a what we call as a MEMS die. Okay, but MEMS die is not a single die. Okay, it has a two. So this is a real MEMS is this one. Okay, and this top die is going to be a cap wafer. Okay, so this is a MEMS die. I hope my writing is clear to you. Okay, so ASIC die, MEMS die, and cap die, and you can see the tiny wire bond here. Okay, so this is wire bond, which is basically as a first level package, and this metal is going to be used for a second level of package. Clear? Similarly, this is example of a flip chip. Okay, so instead of using this kind of a wire bond, okay, people can also use this kind of a solder based solder means this is going to be tin, silver, copper. Okay, this is basically a simple solder which is present in this thing in the form of a balls, so you can use it, okay, for interconnection also. Clear? So this is an example of a first level package. Now this is just an idea where people are working on, so I am going to talk about this thing in later on. So this is a future devices in which we are going to have multiple devices on top of each other. Okay, so you can see that 1, 2, 3, 4, 5, 6 dies can be stacked in a vertical fashion to reduce the overall area on a XY plane. Okay, so we are going to talk about this thing a bit later. Okay, so again this is going to be second level of packaging. Okay, so already we have this as a first level package which is available here, and this is a simple PCB. Okay, and you can see that, so all these metal pins here, okay, this is basically as a interconnect. Clear? So this could be a PCB, or people can also use some kind of ceramic carrier. This is going to be the second level of package. So this second level of package provides interconnection between different dies. So for example, this die can communicate with this die by using this particular PCB. Similarly, okay, we have this third level package, okay, which is not so critical, so I'm going to skip it. Okay, now if you look at this is just a simple representation of how we are doing packaging at a chip scale level. Okay, so you have a wafer, okay, you dice it, okay, and then you find out which particular die is working up to our required limit. Then you take a separate die, okay. If you required, you can do some kind of a post processing, okay. Then these are the ready-made available ceramic carrier, okay. So in this example, this is going to be a ceramic carrier, and I have shown a picture here. So this is how a ceramic carrier looks like, okay. So this ceramic carrier is without any die, okay. This is just a plain, simple, dummy ceramic substrate having the proper interconnection. So what we'll do, we'll take a die from here, we will keep it on this side, okay, and then we can either create this kind of a wire bond or flip chip, okay. So here we have a wire bond, okay, and in this example, this is going to be a flip chip, okay, correct. So this is going to be the first level of interconnection, and these pins, if you insert these pins on a PCB, then this will be causing as a second level of interconnections. Okay, so I hope that things are clear to you. Okay, this kind of a pin grid array based packaging is very popular in case of a microprocessor. Okay, and most of us definitely, I hope we may have seen this thing in the real life. Okay, this is also a very popular packaging technology called dual inline package. Okay, so we have a package, okay, and all the interconnections are on the two sides. Okay, so we have a I think 7 here, 7 on other side. So how do we do that? Again, the same process, because we are performing the packaging at a chip scale. So we have a wafer, okay, we will cut it down, we will take an individual chip, okay, and this chip is going to be put on the carrier, okay. So this is going to be a ceramic, okay, and then you can see that we have different pins here, okay, and now what will happen, the interconnection will be formed from this chip to these metal lines. So let me just show you so that things are a bit clear to you. Okay, so what we'll do, so this is a ceramic carrier, okay, we will keep this chip here, okay, and let me just go and make this 3D picture here, okay. So what will happen, so whatever number of interconnection you want, you have to create some kind of a pads here, metallic pads, and then from each metallic pads, okay, you need to have separate wire bond, okay. This thing you have to do it, and individually these wire bonds will be connected to these metal lines. So for example, okay, can you see this 1, 2, 3, 4? So all these wires, they will be basically connected here, okay. So this is what you know as a wire bond connection, which is shown in the below picture here, okay. And once you do that, then you can do some kind of epoxy module, okay, by simple plastic molding process, okay, which we have gone through as a mechanical engineer. And after that, you will simply bend these pins, okay, and you will have a ready-made connection. Okay, so if you look at this example here, okay, we have provided electrical interconnection through this gold wire bond, okay, and then we have provided mechanical protection by this epoxy, okay. So the fundamental function of packaging, the mechanical protection and electrical interconnections are satisfied, okay. So if you look at this example, we are performing the packaging operation, okay, at a chip scale, okay. Yeah, okay, so we are performing this particular packaging at a chip scale. So problem is that, okay, if you have let's say 1,000 devices or 10,000 devices, packaging will be basically happening at a one device at a given point of a time, okay. So of course this process, although this is good, okay, this is going to be time consuming and costly, okay. So let me just show you again this chip scale package and how we perform system level packaging by this approach, okay. So chip scale packaging, how we do perform at a system level. So what will happen? Okay, so let's say that this is a CMOS die. Okay, all these individual die basically represent a transistor. Okay, now what we do? Okay, we take this dicing process. We take a single die. Okay, working die, and then we have this particular chip carrier which is presented in this thing. Okay, so we have got a packaged microprocessor, for example. Okay, after that it becomes, we have to do the second level of package as a pin grid array. Clear? Now this particular device is ready. Then we have a substrate. Okay, this is what you can imagine. There's a motherboard. Okay, so this particular processor will be interconnected on a PCB. Then we have a stack memory because we need RAM, ROM, and all those things, and they may be fabricated by somebody else. Okay, so Intel, for example, is making processor. Okay, Samsung, okay, Hynix, okay, they are basically making this kind of memory. Okay, so if you look at this example here in second image, these memories are also a packaged version. Okay, so inside, if you cut it down, you'll find individual ICs representing a memory chip. But right now, this is going to be a packaged version. So this packaged devices will also be gone on a substrate. Okay, on the motherboard. Okay, so we have a processor, we have now memory. Okay, now we have all this kind of discrete component, resistance, different kind of capacitors. Those will also be packaged here. Okay, after that we need to provide this kind of again connections. Okay, all these batteries, connectors. Okay, they will be basically gone here, and this is how a system basically looks like. Okay. So I hope that all the participants are now at least a bit familiar that what is the chip scale package, okay, or let's call it device level package, and how those different devices are integrated on a printed circuit board, okay, or motherboard, okay, and how they combine together to create this kind of a working system. Okay. So this is example of a chip scale package. So again, I like to mention here that if you look at let's say the cost of the mobile phones, right? If you compare, for example, let's say 5 years or let's say a couple of years before, you might have noticed this particular trend that in the electronics field, especially the consumer electronics field, the cost of the product is going down. Okay, so if you compare, for example, even let's say 5 years before, okay, any good mobile phone, it used to come something 12, 13, 14,000. Okay, but right now, if you look at our current thing, in 6, 7,000, 8,000, we have a working smartphone, which is basically is easily available. Okay, so especially in case of microelectronics, microsystem packaging, okay, all these companies, they are under huge stress to reduce the overall cost of the product. Okay. And how do we can reduce the overall cost? Okay, so cost can be reduced by, for example, at a component level. So, for example, a transistors or microprocessor cost is going down. Okay, but major function or major contribution of the product cost comes from the packaging. Okay, because packaging is going to be very complicated thing. Okay, so in this particular field, people are working on to reduce the cost. Okay, of a from the packaging point of view, and this is where people are thinking to go from a chip scale package to a wafer scale package. So how does it look like? So we have, let's say that we have a same MEMS wafer, okay, but right now this is going to be at a wafer scale, okay, and a wafer can have several thousand devices depending upon what is the die size. Okay, there could be 1,000, 10,000 devices which is basically present on a MEMS wafer. So earlier we were doing the packaging at a chip scale, but right now we have to do the packaging at a wafer scale. So how do we do that? Okay, so as I mentioned to you before, that most of the MEMS inertial sensors, they have some kind of a tiny moving parts, okay, which are very, very fragile. So we need to protect them from an external environment. This is the first requirement from a packaging. Okay, so what we will do, we will take another wafer, either from silicon or glass, okay, and we will bond them together. Okay, so will this MEMS, okay, they will be basically bonded together. Okay, Now, what kind of bonding? So I think a couple of professors in this workshop might have gone through the basic MEMS fabrication process. So we have different kind of wafer bonding, like direct wafer bonding, anodic bonding, metal-based bonding process, which are basically easily available. Okay. So now at this stage, we have covered the first requirement of mechanical protection. Okay. All these dies are mechanically protected. Okay. And after that, what we'll do? We need to provide electrical interconnection. So how do we provide electrical interconnection? We will create some kind of a through holes. Okay. So let me just show you. So let's say that this is a MEMS die. Okay. For simplicity, I'm just representing a cantilever as an example. Okay. Let's say this is a cantilever. Okay. So there could be 1,000 devices, but I'm only going to show two things. So what we'll do? Okay. We will take a similar wafer. Okay, which is going to be here, and according to this die we will create some kind of a capping. Okay, so according to the layout of just a minute, according to the layout of the MEMS die, we will create this kind of a cap wafer. Okay, and what we'll do, we will use this cap wafer and we are going to bond this thing, right? So when you bond it, it looks like this. Okay, something like this, right? Now after that, what we'll do? So right now at this stage, we have provided the mechanical protection. Okay, and now what we'll do? We need to pass the electrical connection. So what we'll do? We'll create some kind of a through holes. Okay, so we'll create some kind of through holes, and these through holes will be filled with copper. Okay, so at this stage, if you look at the animation, we have created through holes, and then these through holes will be filled with some kind of metal. So what will happen? This metal will act as a kind of a electrical interconnection, and it will going to be in all these dies. Okay, so depending upon how many dies you have, you need to optimize it, and you need to provide all kind of a interconnections. Okay, I hope people are getting this point. Okay, so if you look at this picture here, we are providing electrical interconnection also at a wafer scale. Okay, so once this thing is done, so I have finished my job of a mechanical protection and electrical interconnection. Then I can do the testing. I can find out, okay, that which particular dies are working, which are not. Okay, in which case the output parameters are going beyond the set limit. So we can do all kind of a characterization, reliability at this scale. Okay, so only after we are satisfied, then we will go for something called dicing process. Okay, to take out the individual die. Okay, so if you look at here, all these processes are performed at a wafer scale. Okay, it means that the packaging of all dies are performed or carried out at a wafer scale. Okay, and only after that we will do the dicing process. Okay, so because of this particular approach, the cost of a single package die is going to be smaller, lower than the chip scale package. Okay, so cost is definitely going to be the only drawback in this particular approach is, okay, if you look at the previous thing, okay, we are performing the packaging for only those dies which are good, those dies which are basically, in which case the output parameters are within the set limit. Okay, so we will only going to package this thing. Suppose in this example, okay, suppose in this example, let's say that this die, okay, and this die, for example, let's say 3 dies. Okay, they are not working. Okay, we know that these dies are not working, they are damaged. Okay, now we have no choice because we are doing at a wafer scale. So these dies which are bad, they will also be packaged. Okay, so this is one of the drawback of this particular approach. Okay, but overall from cost point of view, this is definitely going to be easier. Okay, so I hope that this information is clear. Okay, one more thing is which is basically going on is what we known as a direct integration of MEMS to CMOS. Okay, so just now I have shown you here that this is the current way by which MEMS packaging is being performed. Okay, so we have an ASIC die or electronics die. Okay, we have a MEMS dies. Okay, and then these are basically interconnected through this kind of wire bond, right? So if you look at this thing, the overall picture, overall the footprint area of a package is going to be this much, this huge. Okay, this is the X, let's say X size line. Okay. Now, if you look at the size of a MEMS, okay, this is going to be roughly about this. And all the participant, this is a real image of a MEMS accelerometer. Okay. So if you look at, you can clearly see that the overall size of a packaged version is about 4 times more than the MEMS sensors. And why it is large? Because the ASIC die is bonded in XY plane. Okay. So if you look at this particular case, there are two problems. The first problem is going to be the overall package size is very large, and second thing is that the interconnection, the path, okay, this wire bond is very long. Okay. So you know that electrical signal, okay, the time taken by any electrical signal will depend upon the length of this particular interconnection, right? So what will happen in this case? If this particular length is very large, okay, the signal delay will also be large. It means that there's going to be some kind of a delay in the sensor and the ASIC response. Okay. Now, such kind of delay can be very, very significant in cases like accelerometer. Okay. So ideally, all the designers and MEMS guys, they want to reduce the overall interconnection length as small as possible. Okay. So this is where the idea here is going on, that people are working on this thing, that instead of going for a 3-die approach, okay, people want to have a direct integration, okay, to a MEMS wafer and CMOS wafer. So if you look at this is still a schematic image. Okay, people are not able to really made it together so far, but this is a kind of an idea. Okay, that if we can take a MEMS wafer and CMOS wafer, okay, bond them together, okay, and then create this kind of interconnection by using TSVs, then what will happen? If you look at this thing, the overall package size is going to be almost same as the size of a MEMS die. Okay, so compared to the previous case, in this case the footprint area is going to be very, very small. It means that in the same mobile phone we have the overall footprint area is small, and we have a possibility to keep more and more functional devices. Okay. Second thing is that compared to this particular wire bond, okay, if you look at if you can compare, so this is the wafer thickness. Okay, you can imagine that compared to this particular thickness of the wafer, the interconnection length is almost double. Okay, but if you create this kind of interconnection within the wafer itself, then the interconnection length is going to be very, very small. It means that the signal will move faster from ASIC die to the MEMS die. Okay, so this is one of the challenge where MEMS packaging guys are currently working on. Okay, so now coming back to these things, I think I've already mentioned to you. So if you look at the standard IC packaging, if you look at any transistors, okay, we are having this microprocessor from almost 20-25 years now. Okay, so IC packaging are becoming more and more standards. Okay, we have companies like AC, okay, Taiwan, Amcor, UTAC. Okay, these are some of the big companies which are only dealing with IC packaging. Okay, so this IC packaging is almost becoming, let's say, standard thing. But when we talk about MEMS packaging, okay, you will not find a single company right now. Okay, most of the guys, okay, who are doing it, the packaging, okay, you will find mainly about accelerometer, okay, mainly about pressure sensors, okay, mainly about the gyros. Okay, so the big challenge here, as I mentioned to you, that the MEMS packaging is considered to be relatively difficult, okay, and not any kind of standard. Okay, the main reason is that MEMS has a very, very small moving parts. Okay, so in case of accelerometer, which is shown here, okay, if you look at this picture here again, this is a famous picture. So these are what is known as a COM drive. Okay, and the width of this COM drive, okay, is about 2 micrometer. So if you look at this case here, okay, width is going to be 2 micrometer. This thickness is going to be roughly about 20 micrometer. This is right now industry industrial. Okay, and they are made out of silicon. Okay, so remember, silicon is a brittle material. Any kind of sudden shock, okay, it will be broken here. Okay, so because of this particular issue, this is going to be very difficult. And other, for example, BioMEMS component, one of the requirement is that if you talk about any kind of a cantilever based devices which are basically used as a biosensors, okay, you need to provide some kind of a interactive interface. Okay, so for example, if you look at this case here, okay, we have some kind of cantilevers, okay, and if you want to test any, let's say, bio species, these cantilevers should be exposed to the input environment. Okay, so packaging needs to provide some kind of a open interface, but other parts need to be completely protected. Okay, so the requirement is completely different in case of MEMS packaging. Okay, then we have something called requirement of hermetic packaging. Hermetic means airtight packaging, especially in case of accelerometers or gyro, which has a moving components, in which you do not want any kind of interaction of the moving parts with the outside environment, or you do not want that the pressure inside this particular cavity should change with respect to time. Okay, so you need to provide hermetic sealing, okay, or airtight sealing, which is not often required in case of IC packaging. Okay, so some of the commercial customized MEMS package, I tried to show it here. Okay, you can see that. Okay, the first picture is accelerometers. Okay, we have if you look at this thing, okay, this is basically a piezoelectric based actuator, which is basically used in our inkjet printing. Okay, so requirement here is a bit different here. This is example of a digital micrometer device from the Texas Instruments. Okay. And then this is going to be a MEMS module. Okay, so you will see that the requirement of this particular packaging are typically different. Okay, so for example, if you look at the MEMS module, okay, so if you look at this which is interconnection, okay, those guys who might have seen this kind of MEMS module, you will see that this is a very flexible substrate. Okay, the substrate here is not rigid. Okay, this is kind of a polymer based substrate, okay, which is flexible, so that you can basically put the whole thing in a very compact environment. Okay, so requirement here is going to be a compact thing. Other cases it could be a hermetic or something else. Okay, so for a particular device, okay, you need to have a particular packaged component. Okay, so I think I have already spoken a bit about how do we package the MEMS accelerometer. Okay, and typically it looks like this. Okay, so again one more time, because MEMS accelerometer is going to be the most famous commercial component. Okay, so we have ASIC. Okay, now it is clear. I hope you can see that this is not a single die. This is basically a packaged MEMS device. Okay, so it means that here we need to provide some kind of a hermetic packaging. Okay, so you can imagine that and see that this is going to be the wire bond. This is going to be the first level of interconnection, and these pins are going to be the second level of interconnect. Okay, or we can say that is the first level package. This is going to be the second level package. Okay, clear? So this is a standard component. Okay, another example of a MEMS gyro from Sensonar. Okay, so again this kind of a ceramic carriers are quite standard right now. Okay, and these are the gold plated pins. Okay, again this ASIC die, and this is going to be this MEMS die, and you can also see some tiny gold wires here. Okay, so these components are becoming now standard, but when you talk about, let's say, pressure sensors, right? Pressure sensor is going to have a complete different kind of package. Let me go through one slide further. Okay, so you can see that all of these are pressure sensors. Okay, but you can see that the packaging of this pressure sensor are totally different. Okay, so you can see that we have two modules here. Okay, so this is a 2 input. Okay, if you want to create any kind of a differential pressure sensor, then you need to provide 2 inputs. Okay, to the medium, or we can have a single tube here. Okay, we can have a tiny components tube here. We can have like this thing. Okay, you can also see that the number of requirements of the interconnections are different. So in this thing we have a 4 pads here. 4 will be on other side. Okay, but depending upon this thing, you have requirement of a larger number of interconnections. Okay, so all of them are basically a MEMS pressure sensor, but the packaging of these things are totally different. Okay, so those who are interested, these images are from the Freescale semiconductor company. Okay, on their website you can take that. Okay, so we have a pressure sensors here. Okay, bottom picture represent about the accelerometer, and I hope that this thing is clear to you. Okay, Now, let me go back to the previous slide. So those guys who are a bit familiar with the MEMS pressure sensor, it basically looks like this. Okay. So we have a MEMS pressure sensors. Okay. Where we have a membrane. Okay. And so then we have this kind of a piezoresistive sensing devices, and in all kind of MEMS pressure sensor we are typically using a wheat-stone bridge kind of a combination. Okay. And then as a part of a packaging, you need to also attach this kind of a tube. You need to provide the input interface. So otherwise, how this particular MEMS pressure sensor will communicate? Okay. So the media whose pressure you want to find out. Okay. You need to attach some kind of a tube. Okay. So this particular medium will go through. Okay. It is going to basically cause some kind of movement of this particular membrane, and as a result, the stress on the fixed end of the membrane is going to change, and by using this kind of a piezoresistive resistor, we are going to measure the change in the resistance as a input of the pressure. Okay. So this is how this is a basic concept of the pressure sensor. But when we talk about the packaging, you can see, okay, the packaging looks like this. Okay, this is a very simple example of a pressure sensor. Okay, so the actual chip is going to be here. Okay, so this is going to be the actual chip, and then you can see that this is going to be some kind of a wire bond. Okay, so depending upon how many provide suitable number of wire bonds. Okay, and these wire bonds, okay, are essential because you want to measure the change in the resistance, right? So for that, this thing is needed. Then, okay, so these wire bond will be connected to these pins which are shown here. Okay, and ultimately you need to provide this kind of metallic cap so that you can protect the pressure sensor. Okay, so this particular metal cap will be soldered on that interface. I hope this thing is clear. Okay, and then this is going to be the main tube through which you can connect and you can basically measure it here. Okay, so this is one of the popular simple pressure sensor, but again, depending upon what is the actual application area, you may have pressure sensor of this shape also. Okay. Okay, so again, I think I've already explained this kind of pressure sensors before here. Okay, so you can provide also some kind of reference pressure also here. Okay, depending upon your choice. So these things are very clear. Okay, now I like to highlight here one of the slide here. I've already mentioned to you that people are moving from the single functional devices to multiple functional package devices in a single one. Okay, so we have a classical example of this kind of Apple Watch. Okay, so this particular picture is about 5-year-old. Okay, so if you look at this thing, okay, the overall package size, okay, is going to be very small. This is something about 4 centimeter, let's call 40 millimeter somewhat. Okay, and you can see that inside this 40 millimeter, you have a multifunctional devices. Okay, so all these things, okay, are a part of a packaging. Okay, whether it's a first level of package, whether it's second level of package, third level package. Okay, but all these things are basically the part of a packaging. So you can imagine that what kind of complexity is involved when you try to create this kind of a miniaturized multifunctional devices. Okay, so you will have all this kind of sensors which are kept on the motherboard. Okay, then you need to provide this kind of batteries. Okay, interface. You need to provide this kind of mechanical protections. Okay, all kind of RF devices. Okay, so things are getting very, very complicated, especially in the coming days when we talk about fabricating this kind of a complicated package device at a lower cost. Okay, so okay, let me go back to this second module. Okay, from 2D to 3D. So I've already mentioned to you. Okay, let me go back a bit further. Yeah, so if I mentioned to you, so what happens is that earlier we have seen that this MEMS die and ASIC die are basically kept on a XY plane, and then they are basically connected to this wire bond, and then they are packaged, right? So because of this approach, XY approach, the area becomes very large. Okay, so idea here is that if we can put all these dies, okay, not in XY plane area, but if you put it on top of each other, then what will happen? The overall size is going to be reduced. Okay, and at same time, the interconnection length is going to be short, right? So in order to achieve this thing, we need certain thing called through substrate vias. Okay, so I'm going to talk about this thing a bit quickly, but let me just show you. So how do we do that? Okay, so when we talk about three-dimensional packaging or three-dimensional wafer scale packaging, the process looks like something like this. Okay, so this is the part of work of when I was in Finland. Okay, this is my team was working on that. So we used to have a 6-inch 150 millimeter wafer. Okay, in which we have about 2,000 MEMS devices. All are basically resonators. Okay, so this is devices. Okay, resonator looks like this. So our task was to do the packaging at a wafer scale. Okay, not at a chip scale. So as I mentioned to you, that when we talk about wafer scale packaging, it means that we need to have a mechanical protection of each and every die, and then at the same time we need to also provide some kind of electrical interconnects so that MEMS die and ASIC die, they can communicate with each other. Okay, so idea is that you take a MEMS wafer, you take another wafer, okay, and after that you need to do the bonding. Okay, you need to attach this MEMS die to this die. Okay, now in case of MEMS resonator, we have to provide a perfect airtight package because we do not want any kind of a leakage, okay, of air to reach there. Okay, we do not want that this pressure which is kept inside this pressure MEMS resonator device, it should basically vary with respect to time. Okay, so we wanted to have airtight package, and for that what we have done something called sealing ring. Okay, so we have this is as an example of a copper tin copper bonding. Okay, so copper tin copper bonding is that, and if I can show you the top view because a couple of you may not be from this area. So we have a MEMS die. Okay, and what we have done, this is a cap die. I'm showing you the top view. Okay, so around the MEMS die we have created this kind of sealing rings. Okay, this sealing ring. Okay, this is called sealing ring. Okay, which is shown here. Okay, so sealing ring is made of copper, tin, copper, like that. Okay, so this bottom copper was present on the MEMS wafer. Okay, copper tin was present on the cap wafer, and when you align them, okay, bond them together at 300 degrees Celsius, this copper and tin, because tin is a low melting point material, it will basically melt and it will make kind of a solder bonding. Okay, so this sealing ring which is shown here, okay, is going to be this part. Okay, it is going to be around the periphery of the complete MEMS die. Okay, so so we have done with our mechanical protection. Okay, and then after that what we do, we have created this kind of a holes. Okay, so inside this cap wafer we have created this kind of tapered holes, and then we filled the hole with copper. So if you look at this orange color, it represents electroplated copper. Okay, now you fill the whole thing with copper and okay, and create this kind of solder bumps. So now you can imagine that so once this thing is done, you can do the dicing process. Now if you want to see that how the MEMS die is communicating with other interface, okay, so you have this electrical signal. Okay, it will basically come to the solder bumps. Okay, because this is also a metal bump, and then it will be going to carry here. Okay, through this conducting wire, it is going to reach here, and then it is going to communicate with the MEMS die. Okay, and similarly, whatever is the output response of this MEMS die, it is going to be gone to the outer world. Okay, so we have a mechanical protection, and using this kind of a technique which is called through substrate vias or through silicon via, okay, we were able to make this particular 3D interconnections. Okay, wafer scale packaging using copper TSVs. Okay, so this part comes under the MEMS fabrication. Okay, and all the remaining part, bonding, creation of this sealing rings, packaging, TSV formation, soldering, solder bumping, everything is a part of a packaging part. Okay, so once you do that, you will have. So there are three important parts for packaging was there. First is that this hermetic packaging or airtight packaging. Second was the copper TC formation, and third was the fine pitch solder bump formation. Okay. And so I'm not going in detail because of time constraints, but this is the final results which I like to show you. Okay, this was the top view of a MEMS wafer, okay, or MEMS chip. Okay, so this is a resonator here. So one resonator is here, another resonator is here. This is going to be the proof mass, and proof mass is supported by 4 springs, 1, 2, 3, 4. So when you apply any kind of let's say frequency, okay, this particular proof mass is going to vibrate. Okay, and this bottom picture shows you the cross-section view of a real thing. Okay, so you can see that this is a real picture of a silicon. Okay, so this is that moving proof mass. Okay, and this is connected to the this device wafer, and this is basically causing this kind of a PSVs. Okay, and this is a chip view picture of a single device. Okay, so all 1, 2. This is not visible. This is the solder bumps. Okay, so that this particular whole stack of the die can be put on the printed circuit board and you can bond them. Clear? Okay, so those who are not familiar with the TSVs process, okay, this is a 3D interconnection things. Okay, and as I just described you, so if you use TSVs as an electrical interconnection, the main feature is that you can stack multiple dies together, okay, in one shot, and then the footprint area is going to be small and electrical signal will take much faster compared to the wire bond process. Okay, so if you look at the dimensions, okay, there are TSVs which are 5 micrometer, there are TSVs which are opening diameter of 200 micrometer. Okay, depth can also vary. Substrates, okay, traditionally people are using silicon as a substrate, but right now this glass is also becoming very, very popular, especially for a radio frequency application. So when you talk about in Indian context, everybody is talking about 5G. Korea is already working on 6G technology. So when you want to transmit all this electrical signal at a higher frequency for a faster speed, you need to switch from silicon to a complete insulative substrate like fused silica, quartz. Okay, so we are going to talk about this thing a bit later. Okay, so if you look at these TSVs are already being used in our stack memory. So whatever flash memory you are using, pen drive, okay, if they're coming from a company like Samsung or Hynix, they will definitely will have these things, okay, these TSVs. So if you look at this memory, what Samsung is doing right now, okay, earlier Samsung, if you recall your previous days, we used to get a very small 512 megabyte. So when I was a student in Singapore in 2005, I bought my first flash memory. Okay, it was only 512 megabyte. Okay, and that time it was something about 50 Singapore dollar. Now after 15 years, okay, in same 50 Singapore dollar, we have 32 gigabyte is easily available. Okay, so you will see that in 15 years the price has really not changed, but the storage capacity has gone up. Okay, and the footprint area has remained the same. So how is it possible? Because earlier people were basically using the XY interconnection, but now they are going in a vertical fashion. So if you look at here, 1, okay, 2, 3, 4, and 5 stack memories are basically bonded together. Okay, so this particular TSVs are very, very important. People have also used this kind of a TSVs in our camera module. So earlier camera modules were very large in size. Okay, this is in 2001, and I think this is in 2010. Okay, so you will see that compared to the previous camera module, okay, the overall size of the camera module has reduced. Okay, its capacity has gone up. Now we can take a very high resolution images easily. The response time has also been reduced, and all these things is happening because of the advanced researchment which is going on in the device area. Okay, so right now we are using this CMOS. Earlier we were using CDMA technology, but also the packaging has also improved a lot. So earlier we were using this kind of wire bond process. Now we are using this kind of a TSVs. Okay, so the TSVs. So if you want to go for a 3D packaging, you have to use this kind of a through substrate vias process. Okay, either you can use silicon or you can use glass. Okay, So now I have 15 more minutes. Okay, so I will try to tell you very quickly the kind of work which we are doing here in IIT Bombay. Okay, I have not included any work of my previous organization where we were working earlier. So in IIT Bombay, as I mentioned to you, that when you talk about in microelectronics or in packaging, we have different kind of substrates which are available. Okay, so we have a silicon as a device substrate. We can have a fused silica or quartz as a substrate. For a second level of packaging, we can use PCB, printed circuit board. We can use alumina, ceramic as a substrate. We can use, for example, other substrate also. Okay, so I'm talking about the first level package here. Okay, first level package means where we have to integrate the device, okay, to the module. Okay, so we have choices. We can go for a silicon or we can go for a glass. Okay, so there's a small difference between silicon and glass. Okay, silicon is a semiconductor. Okay, glass, which is basically a silica, SiO2. Okay, it's a kind of a perfect insulator, right? So problem is that if you try to use silicon in a RF or radio frequency transmission, okay, because of the finite conductivity, because this is not pure insulator, right? Silicon, because we always go for some kind of a doping, so silicon is always going to have some kind of finite electrical conductivity. Okay, and because of that, if you try to transmit this electrical signal at a high frequency, it will have certain losses. Okay, so because of that, people are trying to switch back to fused silica, especially for RF applications. Okay, people are also trying to use this glass substrate in microfluidics application because glass is transparent, right? So if you want to create any kind of a, let's say, chemical reaction chamber, if you use glass, you can basically monitor that what is going to be happening there. Okay, so what we have done, we have basically used glass. Okay, and we try to create this kind of a through glass via or a 3D interconnections. Okay, so what we have done, so basic idea for us that we wanted to create a 3D, 3-dimensional component in the fused silica substrate. Okay, so if you look at this, is just a kind of a schematic representation of a 3D inductor, right? So 3D inductor, which is basically utilized in all mobile phones, you will have some kind of inductors. Most of the time, the inductors which we are currently using is 2-dimensional. Okay, this is 2-dimensional planar inductor, but we wanted to create a 3D inductor. So there's a lot of research activity going on in the area of how to fabricate this kind of a 3D inductors, both in the silicon substrate and the glass substrates. Okay, so we wanted to create this 3D inductor in case of glass. So those guys who are familiar with glass, okay, glass is a brittle material. If you try to create some kind of a through hole by a mechanical drilling process, what will happen? It is going to be break, right? Because this is going to be a brittle material. So the machining of glass is very challenging task. Okay, by a mechanical basis, this is very, very difficult. You can do the machining of glass by laser process, but for that you need a femtosecond laser process, which is very, very expensive. So what we have developed in our lab, there's a process called electrochemical discharge machining process. Okay, so Ankit Ojha, who is chairing this session, he has done his PhD on wire ECDM. So we are also doing similar kind of work. Okay, ECDM process. Okay, so what we have done, we tried to develop a process in which all the required number of holes can be created at same time. Okay, so if you look at the concept here, we created a multiple tooltip electrode. Okay, and using this kind of a customized tool electrode, we have created this kind of a through holes in a fused silica substrate by a process called electrochemical discharge machining. Okay. Now this process is, those guys who are interested in this technology, they can visit my webpage. Okay, we've also put some videos on this process. Okay, but the process looks like something like this because this is a still image. So we have used a multiple tool electrodes, which is in the form of a 3x3 array. So this is an example of 3x3 array holes. You can create 2x5 array, you can create 5x5 array, depending upon how many number of holes do you want to create in a fused silica substrate. You have to first make this kind of a customized tool electrode. Okay, and then we have a counter electrode, and then we have a electrolyte, which is going to be a NaOH or KOH based. Okay, and if you apply a voltage 50-60 voltage, what will happen? There is going to be discharge process which is going to be start here. So you can see there's some tiny sparks. Okay, and these sparks are responsible to create a high temperature, very high temperature on the surface, and that high temperature basically melts the material there. So this is a kind of a very crude way, the basic principle of ECDM process. As I said, those who are interested, they can visit to my web page. Okay, there are a lot of publications here, and I will also be happy to answer these things a bit later on. Okay, so using this kind of a process, and this is a
Sir,
yes.
I have one question. So
Can we take it later? Let me
Yes,
first
sir.
complete.
Yes,
Then we can. I will be happy to answer these things.
yes,
Okay.
sir.
So this is a kind of a process which we have used. This is an in-house developed setup. Okay, which we are using it. And let me show you very quickly. Okay. So as I said that depending upon like how many number of holes do you want to fabricate, you have to first make this kind of tool electrode. So this is example of a 2x5. So 1 2 3 4 5. This is 2x5 array which is used for an inductor application. Then if you want a large number of holes, you can create 5x5 tool tapes, you can create 8x8 array. And then once you use this kind of tool electrode, all the holes can be created at the same time. This is one of the main advantage of our technique, okay, which we are currently using it. Okay. And if you look at the dimension of the tool tip, the tool tip size here is going to be roughly about 150 micrometer. Okay, so it means that the size of the through holes are in order of something about 400 micrometer. Okay, so let me just show you a bit quickly. Okay, so this is the process which is basically carried out at a wafer scale. So this is a 2-inch fused silica substrate. Okay, so we have created using 3x3. First we have created one hole, then we have shifted the XY stage to the second one. Okay, and so on. Okay, so by this particular approach, we can create this kind of a multiple through holes array at the same time. Okay, and this is how the holes look like. Okay, and this is our main wafer here. Okay, so this wafer is basically for a inductor application. Okay, so